Hey guys, welcome back. If you made it to this point, you have taken the endocrine and muscle test, and it can only get better from here. Good job. I'm finishing the hardest test. It should only get better from here. Blood and the heart are awesome. It's actually my very favorite unit, so you better love it too, is what I'm pretty much saying. Just kidding. But let's start on chapter 12, blood, and then we're going to go to chapter 13, the heart. We should get done pretty quick today because this stuff is pretty cut and dry, straightforward. It's a lot of processes, so you won't have as much memorization as you did in the past. So to start, our blood is awesome. We need it. We need it in our body, not outside of our body. It carries oxygen and nutrients to all of our body tissues. It's transportation. I like to think of your vessels as kind of like a highway. Each of your little blood vessels is a truck that gets oxygen and nutrients dumped into the back, and that little truck takes it on your little artery vein highway to wherever it needs to go. Your blood regulates how acidic your body gets because it can take acids away or it can bring buffers to a site, so it regulates that acidity. It prevents fluid loss. So if you are losing fluid, your blood can regulate how much fluid actually goes to your tissues and how much remains in your blood vessels. The biggest one, probably, not biggest, but a big one is white blood cells provide protection for our body. It's our immune system. White blood cells are our immune system. It's how we fight off pathogens that get into our body, fights off the bugs. Lastly, it stabilizes body temperature. So your body's pretty cool, and it knows that when you're hot, it's going to shunt your blood to your skin so it can take the heat out of the blood and evaporate it into the air. It can also like redistribute it wherever it needs to go. So let's say you're sitting in a hot tub and your core is getting overheated. You don't want to cook your organs. A nice cooked liver is not good. So your body is going to actually take heat from your liver or your internal organs that are in that hot water, and it's going to shunt that blood, let's say, up to your head where that heat can like dissipate, or your skin. Most of it just goes to your skin. So it stabilizes your body temperature in that way by absorbing heat and redistributing it to other parts of your body. Your blood is made up of 3 different things. I guess 4 different things. I lied. 4 different things that are main things. 3 belong into one category called formed elements. The other one stands on its own. So the one that stands on its own is plasma. Plasma is not a formed element. Plasma is literally just the fluid part of blood. When you see blood, it's fluid. That's because you have plasma. Plasma is mostly water. Okay, you can donate plasma, make some MOLO. I wouldn't know, haven't done it. Just kidding. Yes, I have because I've been broke. But plasma is just water and contains a lot of proteins. Plasma and proteins. It's pretty much, water and proteins make up plasma. Our other 3, so we had plasma stands alone. The other 3 are formed elements. We have red blood cells, white blood cells, and platelets. So red blood cells function, this is its only function, is to carry oxygen. We need our little red blood cells to carry oxygen for us. Our white blood cells, as I said before, are our immune system. You have a lot of different types. We'll go over those today. They're pretty straightforward, give you tricks for them. And then platelets are not actually a cell. They are little fragments of a cell. So if you had like a red blood cell as a dinner plate, your platelets are like if I took that plate, smashed it into a bunch of pieces, and you just have these little shards of leftover cell. That's what platelets are. They're just little shards of other cells. Okay, so those 3 are your formed elements: red blood cells, white blood cells, platelets, and then plasma is the fluid portion of blood. You have about 4 to 6 liters of blood in your body. It depends on your size. If you're a little person or a big person, you're going to have different amounts of bloods. You don't worry about memorizing that number because it varies between people. Your blood temperature in your blood is pretty warm because remember, it's moving that heat, shunting that heat wherever it needs to go. So it's pretty warm. You can feel that. I don't know if you've like felt someone's blood. I know that sounds super weird. Probably makes me sound crazy, but that's okay. Blood is warm, falls over your hands and you're like, ooh, that's disgusting. Your own blood, when it comes out, if you've like been bleeding, it's like, it's warm, it's gross. I mean, it's awesome. The color of blood. So in your lab and in your class, you'll see arteries are red, veins are blue. Your blood is never actually blue. I know that's a lie. You've been told probably since childhood that your blood is blue. It's not. Blood is red. There's just two shades of red. A bright red is going to be coming from an artery, and a dark red is going to be coming from a vein. I guess I should be more specific and say bright red is coming from oxygenated blood, dark red is coming from deoxygenated blood. That's more specific, use that one. Okay, the pH of blood, how acidic it is. This is one of the most important things that you're going to learn in nursing school. You're going to have this question on tests this semester and next semester and third, fourth, and fifth. Always, this is the number you just want to like burn into your brain and remember forever. The pH of blood is 7.35 to 7.45. Remember that number for here on and forever. Okay? pH of blood is 7.34 to 7.4. 7.35 to 7.45. Sorry, I promise I know it. I'm tired, guys. Okay, viscosity of blood. Viscosity just means how thick your blood is. So because of all the things in your blood, it's actually going to be about 5 times thicker than water. And this is because of 3 things: blood cells and plasma proteins. Okay? If we just had plasma without the proteins or the blood cells, it would just be water. So those plasma proteins and those blood cells, red blood cells, white blood cells, and the platelet fragments all make that blood thick, about 5 times thicker than water, okay? So blood cells and proteins make blood thick. Cool. Let's move on to plasma. That's our first component of blood that we talked about. It is made up of mostly water, like we just said a bunch of times. But it is how a lot of things are transported. If you're not going to hook on to a blood cell, you're going to be taking the little highway of water. You're going to just go down the river. You're not going to be attached to anything. So this is how nutrients travel. This is how waste travel. This is how some hormones travel. So your antibodies travel. They're just in the river of plasma. They don't actually connect onto a blood cell. Your plasma proteins. You pretty much want to know these plasma proteins, especially albumin. So I feel like you're probably tired of seeing my face. So I'm going to draw you a little picture. Here we go. Here is your blood vessel. Beautiful. Okay, in your blood plasma, you have albumin. Albumin, if you have Katie, you've heard this. Albumin, you can remember him as Grumpy Uncle Al. Okay, this is just a protein that's floating in your blood vessel. So you've got quite a few little albumin guys floating around. And Grumpy Uncle Al is negative and wants to pull all the negativity towards him and make everything around him negative as well. So what happens is Grumpy Uncle Al pulls all the fluid from the outside of the vessel into the vessel. Okay, so albumin is in charge of attracting fluid into the blood vessel because he wants to draw in everyone else so he can make them negative too. Okay, this albumin is actually really important because without him, all the fluid would leave our vessels and we wouldn't be able to get any oxygen transported anywhere. So instead, we have albumin that can pull that fluid back into the vessels where it belongs. Globulins, you have two globulins. You have transport proteins and immunoglobulins. So transport proteins literally just do exactly what it sounds like. I'm going to draw it as like a little box. You transport something. Okay, so this is your first globulin, a transport protein. It just transports a yellow dot in this case. The other globulin is your immunoglobulin. So like it sounds, immuno is your immunity, your immune system. So your immunoglobulins float around in your blood, and they go and attack little pathogens that enter that bloodstream. So immunoglobulins are part of your immune system. Another word for immunoglobulin is antibody. Fibrinogen is your next thing that's floating around in your blood. Fibrinogen is just a clotting factor. So this is going to be my little fibrinogens floating around. Fibrinogen is just clotting factor that isn't active until you need to have a clot. Then we're going to go over what fibrinogen actually does. And then you have other plasma proteins. Don't worry about memorizing that giant list. These are your main guys. Albumin pulls fluid in. Your globulins, you have two. You have transport, and then you have immunoglobulins or antibodies that perform your immune function. And then fibrinogen that helps your body clot if you have a break in your vessel. Okay, next we're going to move to our formed elements. Our formed elements are created in a process called hemopoiesis. So hemopoiesis is the formation of red blood cells, white blood cells, and platelets. We're going to start with our red blood cells. You need to know that a red blood cell is a erythrocyte. You're going to need to use those interchangeably. Red blood cell is an erythrocyte. Okay, our little red blood cell buddies look like biconcave inner tube disc things. I don't know how to draw it biconcave. That was going to work a lot better in my head. Doop. There we go. That's looking at it from the side. Here is your little red blood cell. Okay, I'm spending too much time on this. I apologize. They're just so cute. I like the little red blood cells. Biconcave just helps with a few things, and these are important to know. Instead of having a circle, if you flatten it out and give it more surface area by having that little divot, you're giving it more surface area for oxygen to be able to come in and get held in the little biconcave disc. So it just gives it more surface area to hold more oxygen. It also helps them to stack nicely. So if you tried to stack a bunch of spheres or a bunch of like round cells, that wouldn't be super great because you take up so much space because each of the spheres takes up so much space. So instead, they're able to just stack up right on each other, doop, 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 like this. When they go through a blood vessel that's really small. So your capillaries are so small that literally only one red blood cell at a time can fit through. So it's exactly like this. They just get in a nice little row and stack up and move through. They can also bend. So let's say we had a little red blood cell go rogue and it got stacked funny. This red blood cell isn't going to just clog up the whole pipe system. It's going to bend. That biconcave makes it so it can bend to get the blood moving again. Okay, so those are the three reasons why you want that biconcave disc. Larger surface area to hold more oxygen. They're able to stack up and move through the blood vessel nicely. And they can bend so things don't get stuck and they don't get all crammed, like stuck in a pile because they can bend, they can move, they're actively moving through that vessel. This is the only human cell without a nucleus. Okay, red blood cells are my favorite because they're so weird and different. They do not have a nucleus, meaning they can't repair themselves. So as soon as they get made, they have a like exact lifespan and then they're gonna die. They don't have a nucleus. They cannot repair themselves. No nucleus. Also, no mitochondria. Mitochondria are for ATP production, remember? So if we don't have a nucleus, we can't repair ourselves. If we don't have a mitochondria, we can't do aerobic metabolism because remember, glucose breaks into 2 pyruvates. Pyruvates jump into the mitochondria, go through Krebs cycle, pump out a bunch of ATP. Okay, you can't go into that Krebs cycle without oxygen. If you don't have a mitochondria, you can't go through the Krebs cycle, which is good because think about it. If you used up all your oxygen on going through the mitochondria in your red blood cells, you would literally have no oxygen left by the time you reached your tissues. So your red blood cells don't have mitochondria. They only use your anaerobic metabolism, meaning they don't use oxygen. They just use that glycolysis, glucose breaking into 2 pyruvates. Done. That's it. And then the last thing, it contains hemoglobin. Hemoglobin is the actual protein that carries oxygen. Okay, so hemoglobin is the protein that carries oxygen. I'll draw you a little picture here. So each hemoglobin has 4 subunits, 4 little protein subunits. 1, 2, 3, and 4. So these four are hemoglobin. Okay, that hemoglobin, each subunit, so one of these is a subunit. Each subunit is going to contain a heme. Here is my little heme. Okay, so this is heme. Each heme holds 1 iron. My little iron is going to be pink. So here is a heme. The heme is holding the iron. And then each iron holds oxygen. Oxygen will be yellow. O2, O2. Okay, so your hemoglobin consists of 4 subunits. Each subunit contains a heme. Each heme holds onto an iron, and each iron is able to hold onto oxygen. This is important to know the different things that are found in your hemoglobin molecules. So you have protein, you have heme, you have iron, all in each of these blood cells. Okay, so there are 280 million of these little molecules that are each able to hold 2 oxygens in one single blood cell. So I did not do the math, but if you have 280 million of these, times that by 4, that's how many how many oxygens are in one single cell that's a red blood cell. It's insane. And then you have, I don't know how many, actually I do know how many red blood cells. Just kidding, I'm lying. I know how many red blood cells are found in a milliliter. You have like 5,000. You should have around 5,000 red blood cells in like a milliliter. So just mind-blowing how much oxygen is actually held. You don't need to know those numbers. Just know that hemoglobin carries that oxygen, and this is how it does it. If hemoglobin has oxygen on it, it is going to be called oxyhemoglobin. If oxyhemoglobin is there, it's going to be bright red. Oxyhemoglobin means it has oxygen attached and it is bright red. If it doesn't have hemoglobin, if it doesn't have oxygen, it's going to be called deoxyhemoglobin, and that is dark red. So this would be my deoxyhemoglobin without oxygen, and that's dark red. Okay, formation of red blood cells. The formation of red blood cells is called, use red again because fitting. The RBC formation, oops, here we go. RBC formation is known as erythropoiesis. So don't get that mixed up with hemopoiesis. Hemopoiesis is the formation of all three of these cells. Erythropoiesis is the formation of red blood cells. Hemopoiesis is the formation of formed elements. Okay, erythropoiesis occurs in red bone marrow. Okay, that should be a review. Your red bone marrow makes blood. Yellow bone marrow, it's in your book, does not make blood. It's just the red bone marrow. You will go through erythropoiesis, or the formation of red blood cells, when your oxygen consumption is low. So think, red blood cells carry oxygen. If for some reason you don't have enough oxygen reaching your tissues, you're going to make more red blood cells, so you have more little trucks to carry oxygen where they need to go. So if you have an increase in O2 demand, you're going to have erythropoiesis, or poiesis, the formation of the red blood cells. Okay, so cool thing, living in Utah here, we're at a very high elevation where there's not as much oxygen in the air as if we were at sea level. So if someone from sea level comes up here, their body actually thinks that they're suffocating because they're not getting enough oxygen. And you're actually going to form a bunch of new red blood cells. We have more red blood cells here than the people do at sea level because we have an increased oxygen demand because it's not as readily available in our air, which is cool. That's why people come and train here, because at such high elevation levels, I think that's the word. Yeah. Because it increases the amount of red blood cells you have. That way, if you go and compete at sea level again, it's going to be a lot easier for you because you have so many red blood cells that can transfer oxygen where it needs to go. That's why in the Olympics too, I don't know if you saw, people would train, when the Olympics were here, people would train with oxygen restricting masks on so they could build up those red blood cells, so when they came here, they could perform the same as everyone that's been training here their whole life. Okay, you get it. Increase in oxygen demand, you form red blood cells. Okay, for the rest of your red blood cell formation, I am not going to go through each of these. I just want you to know the order that this happens. So your red blood cell starts out as a hemocytoblast. Okay, your hemocytoblast is going to turn into a reticulocyte. Your reticulocyte is going to turn into an erythrocyte. That erythrocyte is going to live, this is RBC, red blood cell. Your erythrocyte is going to live for 120 days. And then after it lives for that 120 days, it's going to break down and be old, and it's going to get phagocytosis or phagocyted. It's going to get eaten, or phagocytosis, by your liver's macrophages. Okay, so this is the life of a red blood cell. No, I hate when this happens. That one didn't go too long. Okay, so this is the RBC life. It starts as a hemocytoblast. It turns into a reticulocyte. It then is going to turn into an erythrocyte, which is a mature red blood cell. That erythrocyte is going to live for 120 days, and then it's going to get broken up by macrophages in the liver when it's time for it to die. This process takes 8 days about, from start to finish. Your hemocytoblast is from day 0 to 4. This is day 5 to 7. And this is erythrocyte is 8 onward to 120. Okay, so if you have a bunch of reticulocytes floating around in your system, that means that you are making a lot of red blood cells. So for some reason, you weren't carrying as much oxygen as you needed. Okay, but know this order. Boop. Know that order of the RBC's life. Okay, erase this. We're moving right along. Okay, for an RBC to form, you need this list. You need protein. Because remember that heme and that subunit, that's made out of protein. So you need protein. What are proteins? Proteins are made of amino acids. So if you see amino acid, don't freak out. It just is saying proteins. You need iron, because remember you had iron connected onto that heme. You need copper. That was not in our little picture, but you need it still. You need vitamin B12. B12 has two things. It has that it needs. It can either have an extrinsic factor or an intrinsic. So the extrinsic factor means that you get its source externally. Okay, and the intrinsic factor is necessary for B12 absorption. B12 absorption. Okay, so if you don't have your intrinsic factor, you won't have B12. So you need intrinsic factor to make blood because you need B12. So this is how your B12 is how your DNA is made in these cells. Okay, so this is your list. You need this list to be able to form red blood cells. Okay, moving on. I'm going to draw you a nice little picture for this next part to help you make sense of stuff. So it'll be just a second. Here we have our little red blood cell. Over here, we're going to have a bone. See if I can. I was so close. Oh, well, you get it. That's a bone. Then you're going to have your liver. Here's your liver. Then you're going to have your kidney. Kidney here. There's your kidney and your intestines here. This is your large intestine. that goes down to your colon. Okay, bone, liver, kidney, intestine, red blood cell. So what happens is your red blood cell is phagocytized, so it gets eaten. Phagocytosis. It's going to break up into 3 different parts. It's going to break into protein. Remember, protein is an amino acid, or protein is made up of amino acids. So that protein is broken down into amino acids. It's going to break into iron, and it's going to break into heme. Okay, protein is the easiest. These amino acids are going to go into your bone, and they're going to be recycled. Okay, iron is also going to go into your bone, and iron is going to be recycled in your bone. Recycled meaning that it's just going to make new red blood cells in that bone. Okay, so protein goes into your bone, it's recycled. Iron goes into your bone, it's recycled. Iron also is going to jump down into your liver to be stored. Okay, so iron goes 2 places. It's recycled in the bone and it's stored in your liver. Heme goes through quite the process. So first, heme is going to turn into biliverdin, which is green. Biliverdin is green. Biliverdin is going to enter the liver, and it's going to be converted in that liver to bilirubin. Bilirubin is yellow. Okay, that bilirubin exits the liver via your gallbladder as bile. Bile is still considered bilirubin. Okay, then that bile or that bilirubin is going to move out to your kidney to get filtered out of the body as urine as urobilins. So it converts again into urobilins, which is yellow, and then that turns into urine. That is why your urine is yellow. Okay, so to start again, we had heme. That heme was broken down into biliverdin, which is green. Biliverdin is converted into bilirubin, which is yellow. Bilirubin is excreted as bile. That bile or bilirubin goes to the kidney and is converted into urobilins. Urobilins is yellow and gives yellow. Urine is yellow color. This bile or this bilirubin also is going to go into your large intestine as stercobilins. This is brown. Stercobilins is brown. You're going to move that stercobilins out as feces. That's why your poop is brown. Okay, so there you go. That's why things are colored the way that they're colored when they leave your body. It's because of your red blood cells getting broken down. So again, your red blood cell is phagocytized. It breaks into amino acids, iron and heme. Your amino acids go into your bone to be recycled. Iron goes into your bone to be recycled and is stored in your liver. Heme is converted into biliverdin before it hits the liver. That biliverdin is green. As soon as it enters your liver, that biliverdin turns into bilirubin. Bilirubin is yellow. Bilirubin is excreted as bile. Bile is the same thing as bilirubin. It's just a different name once it exits that liver. Your bilirubin is going to transfer into your kidneys and become urobilins. Urobilins is yellow, and that gives your urine its yellow color. And then that bilirubin is going to also go over to your large intestines and turn into stercobilins, which is brown, and that gives your feces its nice brown color. Okay, so that was hemoglobin conversion and recycling in your book. Right here, beautiful picture. Moving on to white blood cells. White blood cells, for the sake of today, are going to be blue for all my drawings. So white blood cells are also known as leukocytes. Leukocytes is the same thing as white blood cells. There is also a lymphocyte. This is a type of white blood cell. This is not interchangeable for white blood cell. That trips so many people up because they both start with L. Leukocyte is white blood cell. Lymphocyte is a type of white blood cell. So you have lots of types of white blood cells. You have your like neutrophils and eosinophils. Lymphocyte is just one of those types. Okay? Leukocytes is the white blood cell. Okay, don't get that mixed up because it throws a bunch of people. The purpose of white blood cells is your immunity, immune defense, immunity. Okay, this is how we fight off the bad guys, is our white blood cells. White blood cells have this interesting movement. Most of them are not actually found in the blood, which is interesting because we hook this in with blood. But white blood cells are actually found in the lymph system. So we're going to talk a little bit about the lymph system later. But white blood cells are not found in the blood, they're found in the lymph system. You can find some in the blood. I'm just talking about the majority are going to be found in that lymph system, not in the blood. White blood cells have a little bit of a weird movement. So the first little movement is called diapedesis. Diapedesis is where you have your capillary wall and the little white blood cell is going to squish through the wall and like squish itself out into surrounding tissues. Okay, so diapedesis is the squishing out of the white blood cell from the blood vessel into surrounding tissues. This happens in capillaries. The only place that your blood vessels really have holes big enough for that white blood cell to move is your capillaries. Okay, diapedesis, squishing out of the white blood cell in a capillary. Amoeboid movement, this is like you have your ball of gush, that is your white blood cell, and it like sticks out its little arms and moves itself like an amoeboid. Look up a video, it's kind of cool. It like crawls, the little ball of goop. I don't remember which movie it is, but there's a movie where there's like this blue blob. This isn't helping, but there's like a blue blob that like moves and it like eats everything that comes in contact with it. I don't know. Monsters versus Aliens. No idea. Something like that. Blue blob. If you know what I'm talking about, it helps. If you don't, then I just sound crazy and it's fantastic. So that's amoeboid. It like moves itself. It like is gushy and it moves and it pulls itself and sucks everything inside of it. Chemotaxis is your white blood cell can send out a bunch of chemicals from itself, like little fireworks, saying, oh, I need help. So if a white blood cell sees an infection and it's like, I'm going to fight this infection, but I need my buddy backup, it's going to send out chemotaxis, send out these little signals saying, help. And all of its little buddy white blood cell buddies are going to come help it. Phagocytic means that these white blood cells eat, they engulf. So like I said, the blue blob guy that moves, you just roll over the blob and it's going to like engulf the pathogen inside of itself. Your white blood cells that do this are your neutrophils, eosinophils, and monocytes. The white blood cells that do not do this are going to be your basophils and your lymphocytes. Your white blood cells that do not go through phagocytosis are your basophils and your lymphocytes. Okay, the ones that do are going to be your neutrophils, eosinophils, and basophils. Okay, wait. I said that wrong. Neutrophils, eosinophils, and monocytes. I apologize, I said that wrong. Neutrophils, eosinophils, and monocytes phagocyze their food. The bad guys, they eat them. Basophils and lymphocytes do not. Clear as mud. Yeah, sorry about that. Okay, to start, neutrophils. These are types of white blood cells. Neutrophils are your first type of white blood cell. Neutrophils are your main guy. These are your like main defense. Most of your immunity are these neutrophils. They make up of 50 to 70%. And the normal stuff, neutrophil, normal stuff. I'm gonna write this down so you don't have to keep looking at my face. Whiteboard. Okay, so your neutrophils eat the normal stuff. This includes your bacteria and fungus. Bacteria and fungus. And this one was a phagocyte. Your next one is going to be your eosinophil. Eosinophils eat the eerie stuff. The eerie stuff meaning worms. These also phagocyte, meaning that they eat the worms that they come in contact with. Eerie, another way that I like to think of this one is eerie allergies. Because it also is the thing that gives us our allergies. This is another thing that you're going to, I can't circle it, it's fine, you get it. Eosinophils are our allergies. So this is one of those topics that's going to come up again and again and again. Your eosinophils are your allergies. Okay, it eats the worms, it eats the eerie stuff, but it also is sensitive to your allergen. So when you have an allergic reaction, this is what's doing it. When you're allergic to the pollen in the air and you get those really bad allergies and you get all stuffed up and your body is trying to fight off whatever allergy you had, that's your eosinophil that caused you to be all inflamed and stuffy and nasty because it's trying to fight off what you're allergic to. Okay? So eosinophils are your eerie allergies. Basophils, I'm going to run out of room for my little list here. I'll just start a new one. Basophils are your blood vessel dilation and blocking blood clotting. So that one's not super easy to remember, but it has blood vessel and blood clotting in it. Basophils have two things that are released from them that you need to know. First, they have your histamines is released from your basophils, and you have your heparin is released from basophils. Histamine is going to cause vasodilation, meaning that your blood vessel dilates, your blood vessel gets bigger. This is going to cause swelling and inflammation. Okay, swelling and inflammation is caused by histamine. Basophils are the ones that release histamine. Basophils also release heparin. Heparin blocks blood clotting. So if you are bleeding out and you have heparin, you're not going to be able to clot off that bleed and you're going to bleed all over the place. Okay, so basophils release histamine, which causes vasodilation. Basophils release heparin, which blocks blood clotting. So if it asks which things clot blood and it says heparin, don't get confused by the wording. Heparin blocks blood clotting. It makes it so you cannot clot your blood. Also remember, basophils were one of ours that do not phagocyte. They're not a phagocyte. They do not eat things. They release these two factors that help us fight our infections. Okay, so they are not a phagocyte. That is basophils. I apologize, my list kind of went, and I ran out of room. We are still on your leukocytes. I'm just clearing my list because I ran out of room. And jumping back up. Our next leukocyte is our monocyte. These are your massive macrophages. That just means that they're very big. They're our biggest one, the biggest phagocyte. Remember, macrophages and phagocyte is like the same thing. Macrophages just mean that the cell eats, and the phagocyte is the actual eating. Okay, so a monocyte is a phagocyte. It's a big phagocyte. It's our biggest one. And then our last type is our lymphocyte. This confuses people, so don't get confused. You have 3 types of lymphocytes. You have T cells, B cells, and natural killer cells. These are super important in our immunity lecture, but for now, just know that these lymphocytes have T cells, B cells, and natural killer cells. These are the guys that recognize when you've had a disease before, an infection before. It can recognize you had that infection before, and it can take care of it so you don't get sick with the same thing twice. That's known as your specific defense. Meaning, again, that let's say I had a cold. These guys learn what that cold is. They help fight it off. They learn what it is. And then when that cold tries to enter my body again, they remember that I had that cold. They remember how to fight it, and they take care of it before I can ever get sick again. So you don't get sick with the same thing twice. Okay, so these are super important in your immune system. Remember, lymphocyte is not the same thing as leukocyte. Lymphocyte is different, and these are the 3 types of lymphocytes. Okay, that's our list of our leukocytes. If you have leukocytosis, so cytosis is going to be a high count. Penia is going to be a low count. And poiesis is going to be formation. Okay, so leukocytosis is a high count of white blood cells. Leuko, white blood cell. Penia means a low count of white blood cells. Lymphopoiesis is lympho, white blood cell, poiesis, formation, white blood cell formation or production. Platelets use thrombo. So our leuko was our white blood cells. Our thrombo is our platelets. Okay, so if I have thrombocytosis, we have a high platelet count. If I have thrombopenia, we have a low platelet count. And if I have thrombopoiesis, that's the production of platelets. Okay, know these words, know how to use them, leuko and thrombo, and know the difference between platelets and white blood cells. Okay, platelets, like I said before, platelets are actually just a cell that has broken. It's like that dinner plate you smashed and you just have those little fragments of the plate left. That's what a platelet is. They are just broken megakaryocytes. That's a good word to know, megakaryocyte. So your karyocyte is going to break, this is break, into platelets. Okay, megakaryocytes become platelets. They don't survive very long, but they're stored for like 12 days in the spleen for emergency. Sorry, not the spleen. They're stored all over your body for emergencies. You got to be pretty close. Okay, hemostasis, that's all we are going to go over platelets. Hemostasis is the stopping of a bleed. So hemostasis is bleed stopping. You have 3 phases of hemostasis. Stasis means stop. You have your vascular phase. Your vascular phase, write it, vascular phase is when your blood vessel, so you had your blood vessel, it broke, you had a cut in your little blood vessel. Your vessels are going to like close off and try to reduce the amount of blood that is coming through, getting lost in that little break that you had. So the vascular phase is the constricting of your blood vessel. Your platelet phase is your second one. Your platelet phase is when platelets begin forming a plug over your vessel. So vascular phase, you had your vessel, it squoze off to try to help reduce blood flow where that break was. Platelet phase takes your little squozen vessel here, boop, 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 and starts sticking platelets where you need a plug, okay, to block that blood vessel from bleeding more. So platelet adhesion is when a platelet sticks to the outside vessel. So platelet sticks to wall. Platelet aggregation is platelet sticking to platelet. So like this. So platelet adhesion is to the wall. Platelet aggregation is sticking to itself. Then once these platelets have stuck, you're going to go through your coagulation phase. Your coagulation phase, have a little drawing of it that we're going to do. So I'm going to move my little blood vessel over here. So here is my blood vessel. Okay, I was bleeding out of my blood vessel. There's my bleed. Those platelets that stuck on there, so we've got platelets forming, are going to release chemicals on an intrinsic and extrinsic pathway. Just meaning that one of the pathways is going to come into the blood vessel and one of the pathways is going to go out of the blood vessel to help stop the clot. Okay, both the intrinsic and the extrinsic pathways stimulate factor X. Okay, both intrinsic and extrinsic pathways stimulate factor X. Factor X is going to turn on I'm going to use a little bit darker color. Factor X is going to turn on your prothrombinase. Prothrombinase changes prothrombin into thrombin. Thrombin is going to turn fibrinogen into fibrin. Fibrin is going to block the hole. Okay, it's going to form a clot. Okay, so that might have been a little bit confusing. Let me go over it again. This is your coagulation phase. So to start, your blood vessel pinched off to try to help reduce the bleeding. Then platelets started to plug up that hole that you had made. Those platelets are then going to cause a stimulus in the blood and a stimulus outside of the blood that is going to turn on factor X. It's going to stimulate, activate that factor X. Factor X is going to stimulate prothrombinase to turn prothrombin into thrombin. Then that thrombin is going to turn fibrinogen into fibrin, and that fibrin is actually what forms our clots. So big things with this, know that the intrinsic and extrinsic factor stimulate factor X. Factor X starts our clotting cascade. That's what this is called. And know that this is a positive feedback loop. So once we form a clot, we're going to keep stimulating that intrinsic and extrinsic factor to keep going in this cycle until the clot is completely formed. Blood clotting, you have that like bolded line, super important. Blood clotting is a positive feedback mechanism, meaning that it keeps going and keeps going and keeps going until the problem is solved. And that is to reduce the blood loss as quickly as possible. Okay, so it's positive feedback because you want to get that hole plugged as fast as you possibly can. Okay, this is stopped by three things: anticoagulants, heparin, and aspirin. We already talked about heparin, so that one shouldn't be a surprise. It's released from your basophils. Aspirin is a medication that you take that also stops this process from happening. And then you have anticoagulants. You don't need to know specific anticoagulants yet. You have meds that do it. You have other things in your body that do it. But no, your anticoagulants, heparin and aspirin, block this whole thing from happening. A clot retraction is when you have fibrinolysis, or the slow process of dissolving a clot happening. So clot retraction, is when you have your clot, you had your vessel, it was broken, then you have that clot sitting on top. The clot retraction is when the clot can get smaller and smaller and pull those blood vessels together. Fibrinolysis is the dissolving of that clot. So fibrinolysis is the slow process of dissolving the clot. Okay, you want to slowly dissolve that clot as the blood vessels move back together and heal during that clot retraction, because you don't want to have that clot sit there forever and get sent off in your blood vessels to clog up a vessel somewhere. Okay, so you want to dissolve it so it can heal together without still having that clot on top of it. So that plasmin digests or breaks up those fibrin strands, fibrinolysis. Okay, let's move on to the heart. Heart should go pretty quick. Let's do this, sorry. I've been talking all day. I'm gonna clear this. The heart is my favorite thing in the entire world. I love the heart so much and would love to be a cardiac nurse someday. I'm gonna jump a little bit because I have a PowerPoint that I really like to use. So I'm gonna start in the pericardial membranes and layers of the heart. So if you remember your visceral pericardium, parietal pericardium, all of those things are coming back into play. So you have your heart here, super anatomically correct. On the outside of your heart, that layer that sits directly on your heart is called your epicardium. Epicardium can be used interchangeably with visceral pericardium. Okay, epicardium is the same thing as visceral pericardium. Then sitting on the outside wall of your thoracic cavity is your parietal pericardium. So parietal parietal pericardium. Then floating between your epicardium and parietal pericardium is fluid. Hopefully this is a review. This is your serous fluid. Okay, so epicardium sits on the outside of the heart. Serous fluid separates the parietal pericardium from your epicardium to help reduce friction when your heart is beating. So your heart beats all the time. It's constantly moving. So if it was rubbing up against a wall the whole time, you would have that friction that would destroy the tissue. So that serous fluid keeps that beating heart from rubbing against its neighbor walls. Know that order. Boop. Know this little order. Okay, your actual heart muscle is called myocardium. Myo means muscle, so it's the muscle of your heart. Myocardium characteristics. This is your cardiac muscle characteristics, so this should be a review, but it has smaller cells in skeletal muscle that are branched like this. Boop, 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 boop. Branching off. Yeah, you get it. They're branched. They're smaller than your skeletal muscles. They have a few nucleuses, not a ton, but a few. Where the cells come together, you have intercalated discs. Remember, those intercalated discs are made up of gap junctions that help all of these cells to be able to fire together at the same time. Intercalated discs are linked by gap junctions that allow the action potentials in your muscle to just be able to move from cell to cell without having to depolarize each individual cell, without having to have a neuron touch on each of these cells to stimulate them. Instead, you just have one place in your heart that's stimulated, and the action potential is going to travel through these gap junctions of your intercalated discs and just travel down without ever having to stimulate another cell directly with a neuron. Hopefully that makes sense. Okay, so your intercalated discs are gap junctions that move action potentials without having to stimulate every single cell. You only have to stimulate one part and it will depolarize that entire heart. You have a bunch of mitochondria in your skeletal muscle. So these are my little mitochondria. You've got a bunch of them. You use aerobic metabolism in your heart, meaning you use a bunch of oxygen. Okay, your heart needs oxygen to function. You use aerobic metabolism always when your heart is beating. Okay, if you're resting, you're still using aerobic metabolism. If you're working out, you're still using aerobic metabolism. You never ever want your heart to run out of oxygen. So your heart's one of those things that even if you're tired and you've been working really hard, you're still going to pump oxygen into your heart. It's always using that aerobic metabolism, using its many mitochondria. Okay, last thing, inside of your heart, you have chambers. So here is my chamber. That's not anatomically correct, but you get what I'm saying. The chambers inside your heart are covered by a membrane called endocardium. The chambers inside the heart are covered by endocardium. Endocardium is made up of simple squamous epithelium. Remember, simple squamous epithelium is one layer of flat cells. This creates a really, really smooth surface. So as the blood comes into the chambers of this heart, you are going to be reducing the friction. It's so nice, slippery, smooth, that endocardium, that the blood can just slide by without having any friction, because you don't want your blood to get stuck in your heart. You want it to slide out nicely from your heart. So simple squamous epithelium prevents blood clotting by reducing that friction. Okay, so those are your layers of your heart. It starts your parietal pericardium, serous fluid, epicardium, myocardium, endocardium. Good. This is your myocardium information over here. Okay, is it time to pull out the PowerPoint? I believe it is. Let's do it real quick. Oh, where did it go? Here we go. Okay, here is my heart. This PowerPoint is connected, or should be. I asked Katie to put this on with my video, so she should have it there. Cardiac system. This is actually the PowerPoint I used when I applied to be a TA. So it doesn't like exactly go in the order of your outline, but it hits all the main points. That's why I did the layers of the heart first. Now we're gonna jump into the cardiac system PowerPoint that I used. So super important thing to note, arteries always go away from the heart, while veins always move towards the heart. Okay, an artery becomes a capillary, that capillary becomes a vein. The capillary is like the connection between arteries and veins. It's how you transport from one to the next. Okay, we already kind of went over that. Okay, here is your heart. Going over the anatomy of the heart. With physiology of the heart, you have to know the anatomy of the heart. You need to know how the blood flows. It's a circuit, it's pipes. You need to know how the pipes are formed and where they're going to know why the heart functions as it does. So blood is going to be dropped off into this right atrium. That's your first structure, your right atrium. You have paired on the other side a left atrium. Then the two bottom bigger chambers are called ventricles. You have a right ventricle and you have a left ventricle. These atriums and ventricles are separated by what we call an atrioventricular valve. So you can see atrium and ventricle smooshed into one word. So it's your atrioventricular valve. These also have different names. So this right atrioventricular valve is also known as your tricuspid valve, while your left atrioventricular valve is also known as your bicuspid valve. So how to remember that? When you go to the store, you want to try on before you buy. So right comes first, then left. So you tricuspid first, then you bicuspid second. To make things even more confusing, your left AV valve is known as your left AV valve, your bicuspid valve, and also your mitral valve. It has a third name. Okay, so you could see any of those. In the right side of your heart, you have a valve coming through called your pulmonary valve, pulmonary semilunar valve. This is the valve that blocks the blood from coming back from the lungs. So your lungs are out here, and it blocks the blood from being able to come back in from your lungs. Your pulmonary trunk is where the blood goes through the valve, pop, and goes through that pulmonary trunk. Your aortic valve goes from your left ventricle. So just like this pulmonary valve, your aortic valve is on that left side. It is going to block blood coming back from your aorta, and it's on your left side. Your aorta is that main big artery that you have in your body. Your superior and inferior vena cava connect into that right atrium. This is your veins that are going to drain blood into that right atrium. So your pulmonary trunk and your pulmonary arteries here, your pulmonary veins here, pulmonary arteries, I apologize, I said that backwards. Your pulmonary arteries go out to your lungs. Your pulmonary veins are going to come back into your lungs. So pulmonary arteries are coming away towards your lungs. Pulmonary veins come back into your left atrium. Your aorta is connected to your body, taking blood to the body. Your superior and inferior vena cava are draining blood from the body back into the heart. Okay, so your heart, your blood vessels have two circuits. You're picking up oxygen from the lungs and you're dropping off oxygen to the body. And it goes through a cycle. It's going to go from the heart to the lungs to the heart to the body, to the heart to the lungs to the heart to the body. And it goes in this cycle, picking up oxygen, dropping off oxygen, picking up oxygen, dropping off oxygen. This is called your pulmonary circuit. And then this is called your systemic circuit. Your right side is where the blood goes first, right first. And that is going to pump blood into your lungs. Your left side is going to pump blood to your body. That's why the left side of your heart is so much thicker. That myocardium is so much thicker because it has a lot more area to be pumping that blood to. Okay, blood flow of the heart. Memorize this, know this. This is one of those things that you're going to need to know forever. Okay, so blood is going to enter the right atrium through your superior and inferior vena cava. And this is not on this slide, but you also need to know that it's going to drain in from your coronary sinus. So those are the three places that drain blood into your right atrium: your superior vena cava, your inferior vena cava, and your coronary sinus. Okay, through that right atrium, it's going to pass that right AV valve into your your right ventricle. That right ventricle is going to send blood up your pulmonary valve into your pulmonary trunk, where those pulmonary arteries are going to take blood out to the lungs. The lungs are going to pick up oxygen and send it back through the pulmonary veins into your left atrium. Your left atrium is going to move the blood through your left atrioventricular valve down into your left ventricle. Your left ventricle is going to pump blood out your aortic valve through your aorta and launch it to the rest of your body. Then the body drains it through the superior inferior vena cava, coronary sinus, and it goes through this circuit over and over again. Okay, you need to know where there's oxygenated blood and deoxygenated blood. So your body uses all the oxygen your blood had to offer. So when it's draining up your superior and inferior vena cava, you're going to have deoxygenated blood, as shown in blue. Okay, you didn't pick up oxygen from your atrium to your ventricle, so it's still deoxygenated. You move up through that pulmonary valve to your pulmonary arteries, to your lungs, to go pick up oxygen. And once you have oxygen, you're going to have oxygenated blood move through your pulmonary veins. This is the only time in your body where an artery has deoxygenated blood and veins have oxygenated blood. Okay, this is the only instance in your body where that happens. Okay, so the pulmonary veins are going to take oxygenated blood into that left atrium. You didn't use oxygen from your atrium to your ventricle, so it's still oxygenated. And then you launch that blood through your aorta to the rest of your body, where your body can use that oxygen that you picked up from your lungs. So know this blood flow, be able to do this blood flow, write this blood flow down, know where there's oxygen, know where there's not oxygen. This is going to be super important for everything. Like, this will help you a ton if you can get this down now and not dump it. Because I know that first semester you cram and dump. I am no exception. But this is something you don't want to dump. So keep it in your brain. Okay, moving on. So this, like I said, will be posted so you can quiz yourself, use it. Wow, it's really close to the camera. You can quiz yourself, you can use it, you can do whatever you want with that PowerPoint. But hopefully it helps. I'm going to share my screen. Erase that beautiful mess. Coming out of your heart, you have coronary vessels. So you had Right side, atrioventricle, left side, atrioventricle. Okay, so this ventricle had your aorta coming up and out. This is why I used a pre-drawn picture. Hopefully you can tell what this is that you're seeing. This is your aorta. Okay, so blood is going to get shunted from your left ventricle out the aorta. Okay, not all, once this is done pumping, not all the blood is going to make it over the top of this aorta. Some of it is going to fall back down. That blood that falls back down is going to be stopped, that's the wrong direction, stopped by your aortic valve. Okay, so that aorta, some of the blood that was shunted up through the aorta, it doesn't quite make it over the top of the roller coaster and falls back down and hits your aortic valve here. This valve has little holes on the outside that are connected to arteries that go to the outside of your heart. So now we're looking at the outside of your heart. So get rid of these. We're looking at the outside of your heart. These vessels from these little holes in your aorta, when the blood falls back down, it goes through these little holes. These vessels coming off are called your coronary arteries. These are the vessels that provide oxygen to the heart muscle. So coronary arteries give oxygen to myocardium. Coronary veins are going to take that blood back up to a little sac in the back. And that little sac called your coronary sinus is going to drain back into your right atrium. Okay, so again, the blood is shunted, pumped out of that left ventricle up your aorta. Some of the blood doesn't quite make it over the top of the roller coaster. It's going to fall back down, slam shut that valve we had, that aortic valve. And there's little tiny holes by that aortic valve where blood is going to slide out and go through coronary arteries that supply blood to that myocardium. Okay, so that's how the heart actually gets its blood, is through those coronary arteries. These get blocked super easy, so when you have a heart attack, it's because one of your coronary arteries is blocked. And so your heart can't get oxygen, then it starts freaking out, and you have heart cell death. Okay, conduction pathway. I am actually going to jump back to my heart. Just because I like the heart a lot. I'm actually, sorry. Pause just a second. I should have had this before. I apologize. Oh man, I'm trying to find a better picture of the outside of the heart. I thought I could use that picture, but I didn't love it. Now I'm just wasting your guys' time. Oh my goodness. I apologize. You know what? I'm going to just use the picture that I have and just draw on top of it. Okay, we're back. Sorry. So imagine this heart is closed and not open. Okay, how your heart actually contracts is using the cardiac conduction pathway. Your cardiac conduction pathway. Can I draw? Yeah, there we go. I don't know how to erase it. It's fine. It's fine. We're going to just go with it. Okay, so your cardiac conduction pathway is going to start in your right atrium. So it's on the outside. Imagine this is closed. On your right atrium, you have what we call your SA node. Your SA node is the only place in your heart that actually receives a stimulus to contract. Because remember, once you have that stimulus to contract, all the gap junctions, that one stimulus is going to depolarize your entire heart. Okay, so your SA node is the only place that's actually getting stimulated to contract. Okay, that SA node is going to use internodal pathways that travel down your right atrium to cause your AV node to contract. AV, atrioventricular node, to contract. This AV node is going to travel down your bundle of His, which goes down the middle of your myocardium here. Okay, so bundle of His. That bundle of His is going to branch into two different sections like this, called your bundle branches. These bundle branches then go up the sides of your heart like this, and fibers called Purkinje. I can't find how to spell Purkinje, K-I-N-J-E, Purkinje fibers. These Purkinje fibers are found in the ventricle walls. So here's what happens. Your SA node depolarizes. It travels down your internodal pathways. I should probably write that. Internodal, that's not even writing. That says internodal. Your SA node travels down your internodal pathways and stimulates your AV node. Your AV node is going to cause depolarization down the bundle of His. That depolarization is going to go through your bundle branches and then up through your Purkinje fibers. Know this pathway: SA node, internodal pathways, AV node, bundle of His, bundle branches, Purkinje fibers. How this works is your SA node contracts, it travels down these internodal pathways, and then this atrium is going to contract because that depolarization caused the muscle, heart muscle, to contract. So the SA node fires, it causes these internodal pathways to to depolarize, and that atrium contracts. Then your AV node is depolarized. This bundle of His depolarizes, these bundle branches depolarize, and then your Purkinje fibers cause a contraction of that heart muscle all the way down here. Okay, so those Purkinje fibers cause the contraction, and it's actually going to contract up like this. So you're like squeezing out a tube of toothpaste. Those Purkinje fibers contract from the bottom up and squish out the blood, so the blood can squish up and send out those top vessels up here. Okay, so SA node, internodal pathways, AV node, bundle of His, bundle branches, Purkinje fibers cause depolarization of that ventricle. These valves cause it so when blood is moving up, it's not able to go backwards. That was a bad way to explain it, but clean it off. Can't clean it off. Go to the next one. Oh my goodness. Here we go. There. Okay, so these valves, your atrium and your ventricle, you want blood to be able to move in one direction and one direction only. So as your ventricle contracts, it's going to push blood up against that valve, and that valve is going to close. Whew, that was fancy. That valve is going to close off, and make it so no blood can return back into that atrium. Same thing on the left side. Atrium contracts, sends blood into the ventricle. Ventricle contracts, it closes this valve, so blood can only go up through your aortic valve. Blood can only go up through your pulmonary valve. Sorry, I'm seeing if, yeah, there we go. Okay, so that's why you have those valves. Next, we're going to jump to our electrocardiogram. Your EKG or your ECG. You can use either or. This is what you see, your little heart rhythm, beep, beep, is your EKG or your ECG. It looks like this. Bump, doop, 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 bump, doop, 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 bump. Oops, I missed a bump right here. Oh my goodness, that's embarrassing. Bump. Okay, this is the very first bump is called your P wave. So the first bump is P wave. This is where your atria contract. This is monitoring the electrical activity of the heart. So the P wave is where the atria contracts. Then you have your QRS complex. So QRS complex. This is where your ventricles contract. Then to finish it off, we have boop, another bump, and that is your T wave. Your T wave is the repolarization of your heart. Okay, you need to know what each of these different parts of your EKG mean. So the P wave, you need to know that this is the P wave. The P wave is where your atria contract. The QRS complex is the big spike, and that's where your ventricles contract. And then the T wave is the last bump, and that's where repolarization happens. Okay, so I'm going to erase this. Hopefully that was clear enough. Remember your action potential when we did the diagram, you had your graded potential, which jumped into an action potential, which then hyperpolarized, came to. Hopefully that little graph looks familiar. Your heart is a little different than your regular action potentials. Think back to your action potentials. I know it was a while ago, but remember what happened during your action potentials. Your heart is different. What happens is you're at threshold, then you're going to have a depolarization, so the same as this, but instead of just repolarizing right away, you're going to have what we call a calcium plateau. Then it's going to repolarize before it depolarizes. So that action potential definitely looks different than this one. So you need to know the steps of why this happens, why the action potential is so much longer. So remember, depolarization occurs when sodium enters the cell. So sodium is going to enter the cell and it's going to cause your depolarization. Then that same thing here in your normal action potential, sodium entered the cell. But instead of potassium leaving the cell right away, you have calcium that is going to enter the cell up top. Okay, so you have calcium begin to enter the cell. And calcium is positive, so since you have a positive still entering the cell, you're going to have a prolonged depolarization. So just like sodium, sodium's the same as your regular action potential, but we have a new player. Calcium causes the calcium plateau, which is a prolonged depolarization. Then finally, you're able to remove some positive charge from your cell, using potassium, and that's going to cause your repolarization. So sodium enters the cell, it causes depolarization. Calcium enters the cell, causing a deep, prolonged depolarization. Then your potassium is going to leave the cell, causing repolarization. Okay, this just makes it so your heart can't contract too quickly. It gives your heart a little bit of a break before it contracts again. Okay, so each one of these is a contraction of the heart. Hopefully that makes sense. Normally I have a lot of questions on this, but since there's no one like actually here right now, there's not questions. So if you have questions about this, please email me. It can be confusing, but hopefully that makes sense. Hopefully you can think back to your regular action potentials and this makes sense. Okay, clear this. Jump back over to my PowerPoint. Oh, I don't want to be drawing anymore. Erase that. Remember this. Remember your depolarization pathway. There we go. Okay, so in our cardiac cycle, we have a few things that happen. One thing you need to know is systole means contraction, diastole means relaxation. Systole, contraction, diastole, relaxation. You need to get that straight in your head for any of this to make sense. So systole, contraction, diastole, relaxation. So the steps of how your heart pumps blood through. So first, you're going to have atrial and ventricle diastole. Diastole, remember, means relaxation. So this means both your atria and ventricle are relaxed. So step one, you have atrial and ventricle diastole. This is going to just provide a passive filling of blood. If you're relaxed, your chamber's just open, ready to receive blood. So blood is going to passively flow into your atriums. As that blood passively flows, you're going to have your atria fill up. Then you're going to have your SA node, back to our little nodes. Remember, your SA node contracts. It's going to cause this atria to depolarize, and that is step 2. You have your atrial depolarization or atrial systole, meaning your atria contracts. So that atria is going to pump the blood into that ventricle by contracting. Then your ventricle is going to contract. So 3 is your ventricle systole or depolarization. As that ventricle contracts, you're going to have 2 parts of this ventricle systole, ventricular systole. You have part 1. So part 1 is when the valve closes. So remember how I said when this contracts, blood is going to push up against this valve. Okay, so as that ventricle contracts, you have blood pushing up against that valve, and that valve is going to slam closed. Part 1, your AV valve closes. AV valve closes. Sorry, I'm having a little bit of a lag here. So part 1, blood closes this AV valve. Then the pressure builds up so strong in part 2 that you have your ventricular ejection. This just means that your contraction was so strong that you were able to burst through your pulmonary valve and have ventricular ejection. Okay, so this valve, your AV valve, has to close before you have part 2 of ventricle ejection. Okay, and then we go back into part 1 where everything relaxes. When everything relaxes, you're going to have blood fall back down. The stuff that didn't make it over the top of the roller coaster is going to fall back down onto your atrial and your pulmonary valves, and it's going to slam those valves shut. Okay, so that happens during AV diastole because you're relaxed, so blood is going to try to get back into the heart, but these valves are going to slam shut saying, nope, you can't come back. And so blood isn't going back where it doesn't belong. You have these little cords right here connected to muscles called your papillary muscles. The cords are called your chordae tendineae. These are going to cause it so as blood pushes up against this valve, they're not going to be able to do what we call regurgitation, or it's not going to be able to flop back the wrong direction. The chordae tendineae, when the blood pushes really hard up against that valve, the chordae tendineae cause it so those valves close but don't go any further. It pulls them so no blood can get ejected back into that right atrium. Okay, make sure I got everything. Chordae tendineae and papillary muscles, remember those words and remember that they inhibit the backflow of blood where they don't belong. The right and the left side are going at the same time. So I know that we talk about blood flow as it's like right and then left, but both atria contract at the same time, both ventricles contract at the same time. Okay, so your AV valves, both of them are closing at the same time. And then your pulmonary valve and aortic valve, as you are in ventricle diastole, these are both going to close at the same time as blood passively flows from your aorta back down and your pulmonary trunk back down. The heart sounds that you hear, that like lub-dub, 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 is the actual closing of the valves. You don't hear the ventricles contract, you hear the valves close. So your lub is going to be that closing of your AV valve. So the lub happens when you're in part 1 of ventricle systole, blood is getting pushed back against this ventricle and it slams that AV valve closed. That's your lub. Then you go through part 2 where blood is ejected. And then during ventricle and atrial diastole, as all of this relax and blood passively flows back down your aorta and your pulmonary trunk and slams that pulmonary valve and that aortic valve closed, you're going to have your dub. Okay, so lub, AV valve closes during ventricular systole. Dub is the passive flowing of blood back down during ventricle diastole. S3 and S4 you can't hear as nurses, so don't worry about it. You'd have to be like a cardiologist to be able to hear those. Hopefully that makes sense. I know this can be pretty confusing. If you're feeling overwhelmed, that's okay. This confuses a lot of people. These parts of the heart contracting, it happens so fast. It confuses a lot of people. Don't feel bad if you're behind. Watch videos, watch this again, listen to other teachers. Don't get frustrated with the heart. The heart is awesome. It just sometimes takes a second to click. Okay, we are almost done. Power through. Your SA node, this node up here, is going to contract 60 to 100 times. 60 to 100 times a minute. That's a great number to know. Your SA node is going to contract 60 to 100 times per minute. Your heart, your cardiac output, is the amount of blood pumped by a ventricle per minute. So I'm going to share a whiteboard real quick. So cardiac output, this is a pretty important concept to know. Your cardiac output is the blood pumped per minute. This can be found using the equation stroke volume times heart rate. Stroke volume times your heart rate. Stroke volume is the amount of blood per pump, amount of blood ejected per pump. The heart rate is beats per minute. Okay, so your cardiac output is your stroke volume, the amount of blood ejected in one pump, times your heart rate, how many times your heart is beating per minute. If you have, everybody has about the same cardiac output. Every healthy person has about the same cardiac output. But some people have a much higher heart rate than others, but everyone has around the same cardiac output. So how does that work? What happens is your stroke volume, the amount of blood that gets ejected every beat, can either be a really good high number or it can be a wimpy small number. So if your cardiac output is staying the same and your stroke volume is really, really good, your stroke volume is high, let's say, I don't have one that just off the top of my head. Let's say your stroke volume is 80 milliliters per beat, then your heart is beating at 70 beats per minute. Then you're going to have a cardiac output of 5,600 milliliters per minute. Okay, hopefully that makes sense. Stroke volume times heart rate. If your stroke volume is really, really good, let's say you have a stroke volume of 100 milliliters per minute, then your heart rate would only have to be 56 beats per minute to get a cardiac output of 5,600 milliliters per minute. So see how when I increase my stroke volume, I can decrease my heart rate. Vice versa, if I have a high heart rate, I'm going to have a low stroke volume. So they move in opposites. A high stroke volume means a low heart rate. A low stroke volume means a high heart rate. Athletes are the ones that have a really great stroke volume. So they are going to have a really low heart rate because they have a big stroke volume. So they're going to have a low heart rate. That's why you could have like athletes with a pulse of 40 beats per minute when normally regular adults have a heart rate of about like 70 to 80 beats per minute. Okay, so a lower heart rate means you have a healthier heart because you have a higher stroke volume. Each beat is producing more of a pump, producing more blood per pump. That's why you can have a slow heart rate because your stroke volume is so good. If your stroke volume is wimpy and only a little bit of blood is spurting out, then your heart has to pump a bunch of times to get the same amount of blood to the rest of your body. Okay, Starling's law of the heart. We are almost done, guys. You guys are doing great. Starling's law of the heart means the more your heart stretches, the harder it's going to contract. The more the heart stretches, the harder it's going to contract. So if you have more blood coming in, you're going to have a bigger contraction. That's Starling's law of the heart. As the fibers are stretched, the more forcefully it's going to contract. That's kind of the same thing as your venous return. Your venous return is the amount of blood getting dumped into the heart from your veins. So if you have a high venous return, you're going to have a higher stroke volume, meaning your heart's going to contract harder and it's going to contract faster. Okay, so it's going to try to pump that blood out faster and harder. So Starling's law of the heart says if you have more blood returning, you're going to have a stronger contraction. And your venous return, if you have a higher venous return, you're going to have a higher stroke volume because you're contracting harder. And your heart rate is going to go a little bit faster to try to pump more blood from that heart. Your parasympathetic nervous system is going to decrease your heart rate because you're resting and digesting, hopefully Panda Express. Your sympathetic stimulation is going to cause your heart to beat fast because when you're fight or flight, when you're running away from that bear, sorry, you're going to want more oxygen to be able to get to your tissue, so your heart is beating faster and harder. Cardiac reflexes. Your cardiac reflexes is where you have baroreceptors in your heart, in your aorta actually. Your baroreceptors, remember, detect pressure. So they can determine if you have a high blood pressure or a low blood pressure, these baroreceptors. And if you have a low blood pressure, they're going to be like, oh no, we need to up the blood pressure and cause your heart to beat faster. So cardiac reflexes are those baroreceptors saying, our blood pressure is too low, let's pump a little harder. Hormones, your epinephrine, norepinephrine is your sympathetic hormone. So if you have those epinephrine, norepinephrine, your heart's going to beat harder and faster. And then venous return, we already went over. More venous return is going to cause a greater cardiac output, a greater pump, a greater cardiac output by having a stronger pump and a faster heart rate. Okay, we already went over Starling's law of the heart. We are almost done. Your end diastolic volume. Remember, diastolic is relaxation. Your end diastolic volume is how much blood is in your heart when you're done relaxing. So right before you pump, how much blood is in your heart. That's what your end diastolic volume is. The filling time is the amount of time your heart is actually relaxing. So if you have a really high heart rate, you're not going to have very much filling time for that blood to get into your heart. But if you're an athlete, you have plenty of time between, if you're only beating like 50 beats per minute, you're going to have plenty of time for that heart to fill up. You're going to have a really large end diastolic volume that's going to allow you to have a really big pump, big shunt of blood to the body. Hopefully that makes sense. And Starling's law, remember, stretch causes bigger contraction. So essentially what you really want is you want a heart that relaxes a lot between beats and is strong enough to push all of that blood out and up through your body so your heart doesn't have to beat as many times to maintain a good cardiac output. This stuff can be really confusing for people. Like I said, I hope this made sense. Remember, you guys are almost there. Heart is awesome. You guys are amazing. Email me if you have questions. I'm always here to help. Yeah, that's all. Have a good night. Bye.